Today we're going to talk about linear systems in three dimensions. Before we do so, let's review some ideas from before about the trace determinant plane. Here's our main result. Say that we have a two-dimensional system dy dt equals a times y in terms of a 2 by 2 matrix A with constant coefficients. We'll define capital T as the trace of A and capital D as the determinant of A. We have three cases to consider. First, the eigenvalues of A are real and distinct if and only if the determinant D is less than the square of the trace T divided by 4. If D is negative, then our equilibrium point, namely the origin, is a saddle. If D is positive, then our equilibrium point is either a sink or a source, depending upon whether the trace T is negative or positive. And if the determinant D equals 0, then there is either a line of sinks or a line of sources, depending upon whether the trace is negative or positive, respectively. The second case says that the eigenvalues of A are repeated if and only if D equals t squared over 4. If the trace T equals 0, then there are infinitely many equilibrium points. Otherwise, there's just one equilibrium point, and this is either a sink or a source, depending upon whether the trace T is negative or positive. Finally, the third case, the eigenvalues of A are complex if and only if D is greater than t squared over 4. In this case, there's just one equilibrium point, and it is either a spiral sink, a center, or a spiral source, depending upon whether the trace is negative, 0, or positive, respectively. We can place all of this in one condition, in one simple statement, by using the following diagram. Here, we consider a plane that consists of points t comma d that we simply call the trace determinant plane. Here, we consider three cases where we're just going to break this plane into several regions. First, let's say that d is negative. This is below the t-axis. As we said before, the eigenvalues of our matrix A are real and distinct, and all of our solutions will look like saddles. Second, let's consider the case where the determinant D is positive but less than t squared over 4. This is the region below the parabola but above the t-axis. In this case, we have eigenvalues that are real and distinct, where we have sinks if we're on the left-hand part of the graph, that is if t is negative, and sources if we're on the right-hand part of the graph, that is t is positive. Next, let's consider the region above the parabola. This is where d is greater than t squared over 4. In this case, we have complex eigenvalues. We have spiral sinks if we're on the left-hand part of the graph, that is if t is negative, centers if we're along the d-axis, that is if t is equal to 0, and spiral sources if we're on the right-hand part of the graph, that is t is positive. Finally, we can take a look at the boundaries. That is, either we have the parabola, d equals t squared over 4, or we have the t-axis, that is, d is equal to 0. These will correspond to either repeated eigenvalues or zero eigenvalues, where we have sinks if we're on the left-hand part of the graph, that is if t is negative, and sources if we're on the right-hand part of the graph, that is if t is positive. Here's yet another way we can view this proposition. In the first two columns, we take a look at the different cases for the trace. The trace is either negative, 0, or positive, or we can take a look at the determinant. The determinant will either be below t squared over 4, equal to t squared over 4, or greater than t squared over 4. As we just mentioned, these cases will correspond to either real distinct eigenvalues, real repeated eigenvalues, or complex eigenvalues. We can also take a look at the different cases for the equilibrium points y sub 0. In many cases, there's only one equilibrium point, namely y sub 0 is the origin. But there might be others, especially if the determinant d is equal to 0. Finally, we can ask, what are these straight line solutions? These, of course, depend upon the eigenvectors. That is, whether or not we have a basis of eigenvectors for our matrix A. Today, we'd like to discuss linear systems as we generalize all of this to three dimensions. Let's recall some definitions that we made back in lesson 18. Recall that an n-dimensional linear system is a collection of n first-order differential equations. Here, the constants aij are called the coefficients of the system. We have a few motivating questions that we'll try to answer today. Notice that this is an autonomous system because the expressions on the right-hand side of the equations do not explicitly involve t. We'd like to know what are the equilibrium solutions for this system. Next, we'd like to try to find solutions y sub 1, y sub 2 to such a system. How do we do so? And finally, are the solutions to the system also solutions to some nth order differential equation involving constant coefficients p1, p2 through p sub n? First, let's try to introduce some notation just to make discussion of this a little bit simpler. We're going to express everything in terms of an n-dimensional vector, capital Y, and an n by n matrix A. Recall that the product of an n by n matrix and an n-dimensional vector is another n-dimensional vector. In particular, we can express our n-dimensional system of the form dy dt equals a times y, where y is an n-dimensional vector and A is an n by n matrix. Next, recall the following statements are equivalent for any n by n matrix. A is invertible, the determinant of A is non-zero, and the zero vector, y sub 0, is the only equilibrium point. That is, solution for the expression A times y0 equals the zero vector. Any matrix where either of these properties holds is said to be non-degenerate. Otherwise, we say that our matrix A is either degenerate or that it is singular. Recall that a complex number lambda is said to be an eigenvalue for our matrix A if it is a root of the characteristic polynomial determinant of A minus lambda in. We can express all of this out to see that we do find a polynomial of degree n. Up to some leading coefficient that's plus or minus 1, we can then express this polynomial as lambda to the n plus a constant p sub 1 times lambda to the n minus 1 plus so on and so forth times p n minus 1 times lambda plus p sub n. A non-zero vector v such that a times v equals lambda times v is said to be an eigenvector associated to our eigenvalue lambda. And finally, we'll say that our matrix A is diagonalizable if and only if there exists a basis for Rn consisting of eigenvectors of A. We have the following key results. We won't bother to prove these, but we'll just list them in one place. First, if A has distinct eigenvalues, then it is diagonalizable. However, the converse of this is not true. There are diagonalizable matrices which do not have distinct eigenvalues. In particular, say that A is a scalar matrix. Next, the matrix A satisfies a curious equation involving n by n matrices. That is, a to the n plus a constant p1 times a to the n minus 1 plus p sub n times the matrix A plus p sub n times the n by n identity matrix equals the n by n zero matrix. Here, the scalars p1, p2 through p sub n are exactly the coefficients that you find from the characteristic polynomial. Next, if y is one of the coordinates of our vector boldface y, then y satisfies an nth order differential equation. Here, again, the coefficients p1, p2 through p sub n are exactly the same coefficients coming from the characteristic polynomial. Finally, say that y sub I is an eigenvalue for A, v sub I is an eigenvector for A, and y sub 0 is an equilibrium point. Then the function y sub I, which is e to the lambda it times v sub I plus y sub 0, is a solution for our n-dimensional system dyi dt equals a times yi. In particular, if A is diagonalizable, then we can find a basis of eigenvectors v sub I, and hence the linear combination capital Y sub t equals k sub 1 times y sub 1 plus k sub 2 times y sub 2 plus k sub n times y sub n is the general solution to our n-dimensional system. Now, we've seen what happens if A is a diagonalizable matrix, but what is the general solution to our n-dimensional system if A is not a diagonalizable matrix? In order to answer this, let's consider a couple of special cases to gain some intuition. Let's start with an example of a two-dimensional system. We know that we can express this in terms of a 2 by 2 matrix A. In this case, we'll express this as A11, A12, A21, A22. We've seen before that this matrix has the characteristic polynomial lambda squared plus p sub 1 times lambda plus p sub 2, where p sub 1 is negative the trace of our matrix A, and p sub 2 is the determinant of our matrix A. I'd like to also point out that this matrix A satisfies this curious matrix identity, A squared plus the constant p sub 1 times A plus the constant p sub 2 times the 2 by 2 identity matrix I sub 2 equals the 2 by 2 zero matrix. We've also seen that the x and y coordinates of our vector capital Y satisfy a second order differential equation. That is d squared y dt squared plus p sub 1 times dy dt plus p sub 2 times y equals 0, which of course we know that we can express in terms of a two-dimensional system again. We have the following proposition. If A is a diagonalizable matrix, then this means that R2 has a basis consisting of eigenvectors. Hence, we can write the general solution to our two-dimensional system as a linear combination of two straight line solutions. However, if A is not a diagonalizable matrix, then we cannot find such a basis of eigenvectors. In this case, we can find a basis in terms of v sub 1 and w sub 1, where v sub 1 is an eigenvector and w sub 1 is a generalized eigenvector. In this case, we can write the general solution as a linear combination of a straight line solution and a slightly different looking solution that is e to the lambda 1t times t times v sub 1 plus w sub 1. Now, let's introduce some ideas to explain how to do all of this in a slightly more general way, but for three-dimensional systems. We know that we can express such a three-dimensional system in terms of a 3 by 3 matrix, capital A, that you see here on your screen. From linear algebra, one defines the trace and determinant of this 3 by 3 matrix as follows. The trace of A is the sum of the diagonal elements, A11 plus A22 plus A33. Unfortunately, the determinant is a little bit more complicated to write down, but you can see the definition here on your screen. One then checks that the characteristic polynomial can be essentially expressed as lambda cubed plus p sub 1 times lambda squared plus p sub 2 times lambda plus p sub 3. The p sub 1, p sub 2, and p sub 3 involve slightly complicated expressions in terms of the coefficients of our 3 by 3 matrix A, but let's say that p sub 1 is the trace of A, and p sub 3 is negative the determinant of A. Just like with the 2 by 2 matrices, we find a curious identity involving the 3 by 3 matrices. Here, A cubed plus p sub 1 times A squared plus p sub 2 times A plus p sub 3 times the 3 by 3 identity matrix equals the 3 by 3 zero matrix. And finally, we see that x, y, and z, that is the coordinates of our vector capital Y, satisfy a third order differential equation. Here, d cubed y dt squared plus p sub 1 times d squared y dt squared plus p sub 2 times dy dt plus p sub 3 times y equals 0. And it shouldn't be a surprise that we can always express such a third order differential equation as a system of first order differential equations. That is a three-dimensional system. Now, what if we want to find the general solution to our three-dimensional system? Well, as mentioned before, if A is a diagonalizable matrix, then we can find the basis of eigenvectors, and hence the general solution is just a linear combination of straight line solutions. However, if A is not diagonalizable, then we cannot find the basis of eigenvectors. But we can find two other types of bases that will give us the general solution that we seek. First, let's say that we have two distinct eigenvalues, lambda 1 and lambda 2. We'll be a little bit more precise here. We'd like to factor the characteristic polynomial as lambda minus lambda 1 squared times lambda minus lambda 2. In this case, we can find a basis consisting of v1, v2, and w1, where v1 is an eigenvector corresponding to the eigenvalue lambda 1, w sub 1 is a generalized eigenvector corresponding to the eigenvector v sub 1, and v sub 2 is an eigenvector corresponding to the other eigenvalue lambda sub 2. In this case, the general solution looks very similar to what we found before with the repeated eigenvalues for a two-dimensional system. The general solution is a linear combination of a straight line solution, y sub 1, another straight line solution, y sub 3, but then a y sub 2 that involves e to the lambda 1t times v1 plus w1. The final case is when we have just one eigenvalue, lambda 1. In other words, our characteristic polynomial factors as lambda minus lambda 1 cubed. In this case, we can find a basis consisting of v1, w1, and w2, where v sub 1 is an eigenvector corresponding to lambda 1, w sub 1 is a generalized eigenvector corresponding to v sub 1, and w sub 2 is a generalized eigenvector corresponding to the generalized eigenvector w sub 1. Now, our general solution is a linear combination of three solutions. Y sub 1 is just a straight line solution. Y sub 2 is pretty much what we found above, even with the two distinct eigenvalues. That is, y sub 2 equals e to the lambda 1t times v sub 1 times w sub 1. But y sub 3 now is a new solution we haven't seen before. Y sub 3 is e to the lambda 1t times t squared over 2 times the eigenvector v sub 1 plus t times the generalized eigenvector w sub 1 plus the other generalized eigenvector w sub 2. Thanks very much for watching.